This is my video presentation. My name is Marilyn Torres. And this is my MAS4300 video presentation. Right. The problem we'll be doing is number 33 of our collection of homework problems, which is on page 243, number 19. This is a problem on rings. The problem reads, let R be a ring. The center of R is the set X belongs to R such that AX equals XA for all A in R. Prove that the center of a ring is a subring. The first thing that we're going to do is we're going to label our set C to distinguish it as the center of our set. So C belongs to R such that AX equals XA for all A in R. Now we have to suppose that C is a subring of R. We have to prove three things in our proof. The first thing we have to prove is that this is a non-empty set. It has to be non-empty. So we're going to put that 0 belongs to C, which is the center, which is our set. So then we have, since A times 0 equals 0 times A for all A in R, which can also be denoted as for all A in R, that shows that our set is non-empty. The second thing that we have to prove is our closure under our subtraction. In this instance, we will let X and Y belong to C, which is our set and the center of our ring. In this one, we will have XA equals AX and YA equals AY for all A belonging to R, which is our original ring. We must show, in order to complete this part of the proof, that X minus Y belongs to C, which is the center of our ring, and we will prove this by A open parentheses, X minus Y close parentheses is equal to X minus Y close parentheses A. We will start off with our first one. We have A, X minus Y. We will then apply the distributive property, and we will get AX minus AY. Now we will apply our commutative property, and we will receive an XA minus YA because we will change the order. Once we get here, we're going to factor out our A, and we will get open parentheses X minus Y close parentheses gives us A. And this is because since X and Y both belong to C, which is the center of our ring. This part of the proof is done because these two, we achieved our goal. Now, for the third part of our proof, we must prove closure under the operation of multiplication. We must show that X and Y, both belonging to C, which is the center of our ring and is our set, And this will show that A, open parentheses, xy is equal to xy, close parentheses, A. So we will once again start off with our first, we'll get AXY. Here we will then apply the associative property, and we will move the parentheses to open AX, close Y. We will then apply our commutative property, and we will get XA, close parentheses, Y. We will once again apply our associative property, and we will get X, open parentheses, AY. Then we will once again move on to our commutative property, and we will get X, open parentheses, YA. Then we will again move on to our associative property, and we will end up with XY, close parentheses, A, which is the same as our second, which was what we had to prove in order to prove the identity of multiplication. Now, therefore, the center of our ring, which is C, is a subring of our ring R.